Hi, this is constant coefficient homogeneous linear differential equations. Um, this section starts with introductions and Laura talk about what's going on in general, and the examples starts right after. So in case if you want to skip through the introductions, if you know what's going on and you want to see some examples, I'll mention when that's going to happen at this video. It's roughly maybe like after 7 minutes, but I'll mention that in the description below. Thank you. If you see me going through a little bit into the first slides, it's because of I don't want to make it too lengthy as a lecture. I'm trying to slow down when it comes to the examples. So here we go. Constant coefficient homogeneous linear differential equations. Consider the homogeneous differential equation with the y to the power n as derivatives, as you could see. In operator form, we write this as PD y equals 0, where P of t equals d to the power n plus a1 d to the power n minus 1. The operator PD is called a polynomial differential operator. As you can see, I'm trying not to read everything here in detail, but you could slow down and see what's the difference. Okay, let's move on. It is the special case of the general linear differential operator introduced in the previous section that arises when the coefficients are constants. So in this section we are focused on constant coefficient homogeneous linear differential equations. So these numbers a sub 1 all the way up to a sub n minus 1 and a sub n in this section are homogeneous. I'll take it back, constants. Okay. Associated with any polynomial differential operator is the real polynomial p of r equals, referred to as the auxiliary polynomial. So those terms, you're going to see them through the examples and the problems. Auxiliary polynomial. So that's kind of like a quick way to start solving a differential equations of this type, by introducing a new term called auxiliary polynomial. You'll see that in some examples. The corresponding polynomial equation p of r equals 0 is called the auxiliary equation. So this is a polynomial, set it equal to 0, they will call it auxiliary equation. Example. Still, this is in general, even though it's called an example, but it's just like in general way of talking about what is the auxiliary polynomial. As you could see, they're marked, and the auxiliary equation. Write the differential equation y double prime plus 5y prime minus 7y equals 0 as p d y equals 0, p of d y equals 0, for an appropriate polynomial differential operator p of d. Determine the auxiliary polynomial and the auxiliary equation. The differential equation y double prime plus 5y prime minus 7y equals 0 can be written as d squared plus 5d minus 7 multiplied by y equals 0. That is p of d times y equals 0, a polynomial of d as an input times y equals 0. Therefore, the auxiliary polynomial is p of d. We call it p of r equals r to the second plus 5r minus 7. As you can see, all this right here, guys, if you know what you're doing, look at the equation itself, look at P of R, which is called auxiliary polynomial. Take a look. Y double prime, R prime, R to the second. 5y prime, first derivative, 5r, r to the first, minus 7y, r derivative, no derivative, so it's 7. Pretty much the same thing. And the auxiliary equation is when you set it equal to 0 to start factoring and solving, and that should do it. Okay, we're not solving, we're just writing. We're writing these two formats, this format right here in red and this format right here in green. We're just looking at this. If you take your time, that's what you do, but you'll get used to it. Let's go over a theorem. Still quick, I'm gonna go over it quick. You know the concept from earlier chapters. If P of t equals P of 1 t, P sub 2 t, all the way to P sub kd, where each PID is a polynomial differential operator, then for each I within your limit from 1 to k, any solution to PID y equals 0 is also solution to PDY. So any solution to this right here will be a solution to this. Any solution to this will be a solution to PDY. So the differential equation d minus r to the power my equals 0. Notice the focus here is on r and m. R, which is called kind of, when I call it roots for now. M means repeated. So if you have the second, we'll say d is repeated twice, and so on and so on. So let's focus on the roots and the repeated factor. M is a positive integer, like 2 for the word repeated twice. R is a real or complex number. The roots could be real or complex. Has the following m solutions that are linearly independent on any interval. E to the rx, that's in general. R could be complex. X e to the rx, x to the second e to the rx, all the way to x to the power m minus 1 e to the rx. If you count these guys, they are m solutions. Why? Look at m right here, m minus 1 on top of x. Now dot 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 going backwards to 1 0. So if you read m's from 0 to m minus 1, it's m terms. Okay, once you have repeated roots, see this is repeated, the generic solution, the general solution for our system of equations with constant coefficients are of the form e to the rx. Once you have repeated, you just keep going till you end up with this number of solutions, the m. And every time you repeat yourself, you enter another x. No x, 1x, x to the second, all the way. We're gonna see that in examples so clear. But that's one idea about repeated roots, real or complex. Consider the differential equation d minus r1 to the power m1, d minus r2 to the power m2. So this root repeats m1 times, this root r2 repeats m2 times, whatever m2 is, and so on. Positive number, of course, all the way. Okay. The solutions that are obtained due to a term of the form d minus r to the power m depends on whether r is real or complex. How do you write the solutions? It depends. We are gonna see both. In general, they look like e to the rx, but r could be complex. We consider the two cases separately. Let's take the real one. Real roots of the auxiliary equation. We'll take also after that the complex roots of the auxiliary equation. We'll take it one by one. So let's look at the first case. Real roots of the auxiliary equation. each factor of the function or the form d minus r to the power m, where r is, I'm missing an e here, r is real, contributes the m linearly independent solutions. Let's take a look. Okay, when it's r as real roots, you go from e to the rx, 1x now here involved, e to the rx, e to the rx, and x to the power m minus 1. So this is x to the power 0. If you start counting how many x's, how many terms, x to the power 1 all the way to x to the power m minus 1. From 0 to m minus 1, it's m terms. Okay? Complex roots of the auxiliary equation. This is interesting, and I'll show you what's behind it and how do they deal with it and change it to real roots. Since complex roots of the auxiliary equation occur in conjugate pairs, each factor of the form d minus r to the power m, where r equals a plus ib, where b does not equal to 0 to keep it complex, must be accompanied by a term d minus r conjugate to the power m. These complex conjugate terms contribute the complex valued solutions. A to the power a plus minus ibx, and you keep repeating yourself times x to the second all the way to m minus 1 of the term x. Okay, so the roots are a plus ib and a minus ib. We're gonna go all the way. Let's see some practical examples in a few slides coming. But before that, we're gonna have to give you more details about how do you break this down. For example, we're gonna use Euler's formula, and we're gonna break down the real parts out of it. So just be patient, I'm almost done with the introductions. Here we go. Real valued solutions are obtained in the following manner. Consider the two complex conjugate solutions. If this is a complex solution and this is a complex conjugate solution, this will be written this way. That's Euler's formula. X to the power k, e to the power a x, and then inside we have cosine bx plus I sine bx. For the one that has a minus, it's the same thing except the minus instead of the plus inside, where k goes from 0 all the way to m minus 1, as I mentioned earlier, for m minus 1 for m terms. This is Euler's formula. E to the power ai bx equals e to the power ax cosine bx plus I sine bx. In case this number on top is complex, you just find the derivative the normal way. You bring it down and you keep it on top. That's how we do it with real numbers, but also works for complex. Those are two notes to keep in mind. Since these are both solutions to a linear homogeneous equation, any linear combination of them is also a solution to the equation. What do we mean? Let's take a look and I'll show you quickly. See this right here? This is a solution, this is another solution. Do you remember when we used to say c1y1 plus c2y2? Any linear combination will be a solution. So if you combine these two somehow and cancel the sine bx, you'll get the cosine bx, maybe 2 times. You divide by 2. If you subtract these two, expressions, if you want to call them. This becomes plus, so you have two of these guys, and this will cancel. And that's the game for the next slide or two. In particular, defining y1 and y2 by the following. Notice when I said you add them up. When you add them up, the sign cancels, but you get two cosines, so divide by 2, that's what you do. Now, by doing this kind of combination, no more imaginary part, it's just a real part. Let's build another real part. In case you subtract them, you're going to get twice the sign with an I. To cancel the I and the twice idea, you divide by 2i. And that's what you get. Respectively yields two corresponding real valued solutions. So we'll just take advantage of Euler's formula that displays both parts. We'll take both parts as our two new real solutions and we'll be done. Determine the general solution to y double prime minus y prime minus 2y equals 0. So we know that the general solution will look like e to the power rx. We know y prime equals r e to the rx and y double prime equals r to the second e to the power rx. And we're gonna plug these in the equation one by one. Here's e to the rx, here's r e to the rx, and here's r to the second e to the rx. Using algebra steps, simplify, factor out e to the rx after, we get the following. If you noticed, this is like a lot of talk. Later on, you're gonna get used to it. Look at this and look at this right there. This is what we care about, to factor and find the roots. But it looks like this, if you can. If you can't do it, you could skip those steps. Y double prime r to the second, y prime r minus 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 2 minus 2. No derivatives, so no r. The auxiliary polynomial is p of r equals r to the second minus r minus 2, which gets factored to r minus 2 and r plus 1. The auxiliary equation has roots of 2 and -1, so that two linearly independent solutions are. Remember the way it looks like, they look like this. We're gonna plug in -1 and plug in 2, and we'll gonna write the general solution right after. So here we go. y1 will be e to the power 2x and y2 will be e to the power minus x for minus 1. Now the general solution is, because that's the question right here, find the general solution, will be a linear combination of this and this. And here we go. C1 e to the power 2x and C2 times e to the power minus x. Let's take some more examples. Here's another one. Determine the general solution to y double prime plus 6y prime plus 25y equals 0. Different numbers, and we'll see what's going to happen. First example was distinct, -1 and 2. Usually the other examples will have different ideas in it. So let's see what's this one about. The auxiliary equation is, see where I'm skipping the steps. You could do it. Think about it for a second. Okay, let's go. R prime plus 6r plus 25 equals 0. You could reduce your steps. Oh, this one is complex. So the first one was distinct real, this one is complex, and complex will walk in conjugates, -3 plus 4i and -3 minus 4i. We're gonna use the ideas before, just like a few minutes ago, and we'll apply. Two real valued linearly independent solutions are the following. We use auxiliary, we use the Euler's formula, and we use the linear combination. See if you could remember. We're gonna write them one by one without the lengthy complex solutions. Remember when they were called W1 and W2? After the linear combination, we just picked up the real parts only. Okay, I'll give you a hint. The first one will talk about cosine, and the second one will talk about sine. That's pretty much it. One for cosine, one for sine. When we cancelled one's sine and one's cosine. Okay, let's go for the cosine. E to the power ax cosine bx. Here we go. Y1 will be e to the power minus 3x. That's my a. This is my a up here. Cosine 4x, and that's my b right there. A plus minus bi. I think since you see the first one, the second one becomes so handy. Y2 is e to the power minus 3x sine 4x. So in case if you have complex roots, this is a quick way to write two real solutions. See, that's why I'm slowing down here, because to you guys, this is mainly what you were waiting for. You want to see this in less work and in a regular speed, not too fast. Right? So I hope this is clear. Let's write the general solution now. You know what to do for the general solution. General solution, you want to write them together with linear combination. Here we go. The general solution is, that's it. You just write this right here, write this right here with C1, C2, linear combination, and that should do it. Hopefully this is clear. Work in one slide, as you could see. Of course, we're skipping the algebra steps here, factoring, using the quadratic formula. We want to get to the point. That gives you auxiliary, gives you two roots. Break it down to two real roots and combine them to call it general. Let's take another example. Solve the initial value problem. So another thing, once in a while we're gonna have to practice initial value problem. So it's not gonna be called general solution, it's gonna be a unique solution for that particular case. We know what's P of R. Look at it quick. We're skipping steps. R to the second 4R plus 4. We're gonna set it equal to 0 and find the roots. Factor it, R plus 2 to the second. So we have repeated root now. Repeated root. First example was distinct. Second example was distinct but complex. Third example repeated. And if you remember a while ago on this video, we talked about minus r to the power m. So we have repeated m times. This time m is 2. So we're gonna apply the repeated feature right here. The two linearly independent solutions are, you know, the first one, minus 2 goes for r, e to the power rx. Let's take a look. Yes, when it's repeated, do you remember I was pointing to the x's, x to the power 0, x to the power 1, x to the power 2, all the way to x to the power m minus 1. So now we're gonna bring it back up and keep adding x's, but we're not gonna go like m times, like if m is 7, m is only 2. So here we go. You see this x? Clearly stated. It's bold. This is how you list two solutions, because you have to have two solutions. You know, in higher math, when we factor a polynomial of second degree, we say we have two roots. Even so, sometimes it's called one repeated. It touches the x-axis and goes on. But for us, we consider it two roots. And we have to keep it in mind. All right. The general solution is just combine them with coefficients C1, C2, and you'll be done. So the main feature is this x right here. Repeated. You repeat yourself, but you add an x because it twice, repeated twice. Now, let's go for the rest of the question. Sometimes because we're used to do this and we move on, we forget that there is an initial value problem. We move on. We're gonna find what is C1 and C2 with these two conditions and call it the unique solution. So let's move on quick. Y0 equals 1, y of 0 equals 1. Imagine you plug in 0 here, that's 0, that's 0, that's 1, that's 1. 0 here will cancel the whole thing here, and that's a 1. So C1 has to be 1, because y of 0 is 1. I'll leave the algebra steps for you, but we have to move on. As you could see, we take this one and take advantage of it for C1 and we put it right there, right here. Now we're gonna find its derivative, so I could use this given information and we'll apply y prime of 0 equals 4 to target C2. That's y prime. We use the product right here, product rule. That's why you have more terms. Plug in 0 everywhere you see x, and that will reduce and give you C2 equals 6. We go back and put them back in, 1 here and 6 here, and the unique solution to the given initial problem is 1 and 6 instead of C1 and C2. Okay, here's another example. Determine the general solution to y double prime, y to the third derivative of y plus 3y double prime plus 3y prime minus 7y equals 0. Kind of lengthy, huh? We're gonna have to sometimes deal with third degree and be able to factor. The auxiliary polynomial is, one more time, we don't have to write all the details earlier, we just move on. This is P of R. Take a look. Makes sense, right? Okay, now, if you factor it, you end up with the following. How to factor it, as I said, there is techniques of factoring. There is two theorems for that. This is a formula, known. Or you could use the coefficient and the constant factors and move on. I'm just trying to remind you how do you get this if you forgot to practice. Alright, we set it equal to 0. And we get, this is one root and this will give you 2. 1 real and 2 complex. Minus 2 plus and the minus 2 minus. So that's why I call it 2 complex. I believe the first one gives you e to the x or e to the power 1x because r is 1. We're gonna get the real solutions out of this from Euler's formula and the linear combination earlier. So think with me how we're gonna write them down one by one. Alright? We're gonna use cosine. We're gonna use sine. E to the power ax and cosine bx. B and a. y2 equals, since this one is called y1, I have to call this one y2. E to the power minus 2x, that's my a, and that's my b right there. y3, this gives me y2 and y3. y3 will be the same, exactly the same, except instead of cosine sine. You see guys, I'm slowing down right here because I believe that's what you want me to slow down on. And if I slow down too much like this on the first few slides, which you could read and pause, that's gonna help. So hopefully you understand guys. It's kind of hard to cover those examples without lecture notes. We're missing those days in classroom, and we need to slow down to see the whole picture, and we'll slow down on some examples. Let's write the general solution. The general solution is just a linear combination of these three, and we'll be done. I'm not going to read it. Take a look at it. Here we go. Okay, let's take another example. Now this one is in a different format given to you, which helps because they're giving you everything. You could write from the D operator to the auxiliary with R so quick from this format. Let's take a look. That's P of R. Looks the same. Set equal to 0. It's already factored. That's kind of nice. And we're gonna treat with real, complex, and repeated. And let's move on. The roots are, first one is clear, R equals 3. The second part gives you complex, but without this 2 here, you're gonna get -1 plus I and -1 minus I. Because of this 2, you're gonna have to repeat yourself. Now how do you handle that in solutions and write it down? First one is simple. We're gonna go step by step. So let's break it down. Here we go. The linearly independent solutions are, first one, e to the 3x. Next one, doesn't matter in order which order you want to start with, you're going to use cosine or sine, and e to the power minus x for a part, and cosine 1x instead of b, which is 1. So let's go one by one, and we're going to repeat ourselves. Remember, when we repeat ourselves, what do? Here we go. y2 equals e to the power minus x cosine x. y3 of x equals x times. You see, I'm using the same style to show you that this repeats because each real root that comes from this right here, I have to repeat myself, and every time I repeat myself, I have to introduce an x. I think we're almost done, guys. We're almost done. The fourth one on my list will speak this way with sine. Here we go. And we need to repeat that. So we're gonna add x up front. The general solution is add them all up and add coefficients C1, C2, C3, C4, C5. Alright? All what I'm doing is I broke it down here clearly for you so you could stay focused with me. Write them down. That's C1, Y1, C2, Y2, all these guys. Okay? And that will be the general solution. Let's take another example. We have time for another example. And it's important to practice enough with these guys. So this is a good practice, by the way. It covers enough ideas. Determine the general solution to d to the third, d minus 2 to the second, d to the second plus 1 to the second, y equals 0. Kind of lengthy, I know. Let's write P of R. Here's P of R. Set it equal to 0 and give me the factors. The first one is R equals 0. Multiplicity of 3. Don't forget that. It's right here. It's like 0, 0, 0. We can't ignore it in higher math. Lower math, we just say like root equals 0. We don't say repeated. R equals 2. Well, this one will give me R equals 2 twice. And that's going to give me complex. So here we go. For the first one, we're going to have y1 equals 1. Because R is 0. And because it's repeated 3 times, multiply by x to move to the second one. Multiply by x again to move to the third function. Okay. Any constant will do, but we picked one for this one. Let's look at the second one. R equals 2 multiplicity of 2. We have y4 and y5. We have to move on and keep giving new names now. E to the power 2x and e to the power 2x times x because it's repeated. Let's go for the third one. R equals plus minus I multiplicity of 2. That means a is 0 and b is 1. We're going to consider the cosine and the sine. E to the power 0, we don't need it, which is 1. Then we're going to move on to 2 more with x's involved. y6, see this is y5 we stopped at, we call this one y6 cosine x, y7 x cosine x, y8 equals sine x, y9 equals x sine x. Almost done, guys. The general solution will be a linear combination of all these. I'm not going to read the whole thing. Trying to use different colors to highlight things for you. That's coming from this. And these two in red. And these are in blue. And that should do it. Hopefully the examples were helpful, but I had to start with the auxiliary operator and polynomial and so on, derivative operator. That's it for now. I will start working on 8.3 and 8.4 within this week. Thank you for watching. I hope that it was helpful. Hit the like button if you like it. Subscribe, comment below, and if you like this video, hit the bell icon to be notified when I upload new ones. Until next time, peace. JaberTime.